thank you to CSIRO. I think that's very kind. And since we are a minute over, I think we'll just get going. So Lee's going to kick us off. I will just click you into your presentation.
Thank you.
Okay.
Good morning, everyone. I'm Lei Zhang, a postdoctor currently working at Swinburne University to search and studying pulsars in globular clusters with fast and meerkat. I slightly adjust on the title of my talk today to make it a bit broadening. First, globular clusters are one of the oldest cellular bodies in the universe and the ideal environment for the information of exotic compact stars due to their ultra-density cores. Even more exciting is the potential to find the first millisecond pulsar battery, or perhaps even a stellar mass black hole pulsar system in a globular cluster. Since the discovery, the first globular cluster pulsar in M28, 150 pulsars had been discovered by 2080. However, Talk and Norma 2030 estimate that the galactic globular cluster could potentially host between 600 and 3,000 observable pulsars. So the question is, where are the remaining pulsars? Since before 2080, the major telescopes for globular cluster science are Arecibo, GBT in Northern Hemisphere, and PARCS in Southern Hemisphere. Since 2080, the most sensitive radio telescope in the Northern Hemisphere is FAST, located in Guizhou, China, and in the Southern Hemisphere is meerkat, located in Karoo Desert in South Africa. Fast globular cluster survey began in 2018 under the leadership of Professor Dini here. Nowadays, more than 60 pulsars have been discovered to date. Among them, I need the discovery of the pulsar M5G. M5G is a millisecond pulsar in a compact battery system discovered with the FAST in 2019. After discovering this pulsar, we organized the follow-up timing observations for all known pulsars in this cluster. By combining fast observation with the Arecibo archive data, we obtained the phase connector timing solution spanning up to 3 decades. This is the first successful fast Arecibo collaboration in studying globular cluster pulsars. Furthermore, we carried out a multi-beam wavelength study and n-body simulation, which reveals this globular cluster being affected by tidal interaction with the Milky Way, including significant mass loss and at least one stellar tidal stream. Since 2020, the Trampan globular cluster survey has been making use the full array of the meerkat array to observe the 28 globular cluster as listed in this table. More than 100 pulsars have been new pulsars have been discovered to date. I participated in the discovery new pulsars in 9 globular clusters and needed the discovery of NGC 6397b. And this pulsar NGC 63779b is a very faint millisecond pulsar in eclipsing binary system discovered with the FAST and then confirmed with the Meerkat. This pulsar has the longest orbital period among all eclipsing binary system. Also has X-ray component. So this pulsar also suggests as a hidden millisecond pulsar in X-ray observation. Moreover, the excited radio quiescent phenomena, this pulsar has like half a year, it just cannot see it. So it make it a very strong transitional millisecond pulsar candidate. Yeah, nowadays just three this kind of transitional pulsar discovered. So this pulsar should be very deserved to follow up if it can be confirmed as a transitional millisecond pulsars. The discovery of NGC 6397b potentially relieves a subgroup of extremely faint and heavy obscured binary in globular clusters. Where are we now? Before 2018, the major telescope for globular cluster pulsar science are Arecibo GVT in Northern Hemisphere and FACS in Southern Hemisphere. Since 2018, FAST and Meerkat are real game changer for globular cluster science. The pulsar population in globular cluster has doubled in just a few years. On July 21, back to 2 years ago, my first day at Sweden, my supervisor, Master Wells, showed me a powerful Meerkat and say, "You come to a right place." Since then, I have joined two large Meerkat projects. One is Champion, which focuses on searching for radio transients and pulsars, and Meltan, which focuses on high precision pulsar timing. Within those, I involved in three globular cluster subjects. Marks as the red lights. Yeah, so I have, since this day, I have also started thinking about do a pulsar polarization sensors using both Meerkat and FAST data. We selected on globular cluster based on two points. First is those globular cluster must host multiple pulsars. This lend us the major polarization properties and rotation measurements across the cluster to studying both the magnetic field in the clusters and the small scale magnetic field in the galactic field. Also, we need for polarization data and reliable timing ephemerals, which allowed us build up high singular to noise ratio polarization profile. From all the globular cluster observed by FAST and Meerkat, we selected 5 with Meerkat and 3 with FAST. This figure shows the distribution of selected globular cluster in this or in the Milky Way. During the data analysis, an interesting problem shows up. Those plots show the polarization profile for 4 pulsars in globular cluster M15. The red line means the linear polarization, blue line is the circular polarization, and the black line is the total intensity. Compare the polarization profile from FAST and the previous work from the RCBO. We can see the circular polarization, the blue line, is opposite. Why cause that? To investigate this issue, I compare the polarization profiles from several pulsar timing array pulsars, which observe the every radio telescope. I found that the FAST, PAX, and the Meerkats all use the same definition of stock parameters and the same instrumental basic conventions. Was in contrast, RCBO and GBT use a different conventions. So to make it simple, we can remember the rule as AP-RASC, just like the name of our conference. To summarize, this work represents the first combined effort between Meerkat and FAST. We carried out a polarization synthesis of 46 pulsars in 8 globular clusters, which doubling the number of lower rotation measurements and improving dispersion measurements position by a factor of 8. Surprisingly, we found no evidence of intercluster media in our sample, suggesting the gas is efficiently removed by pulsar wind or stellar radiation. This work was also selected as the science bulletin cover story in May, highlighting how the north and south synergy of FAST like water and Meerkat like fire, because the FAST located in Guizhou is quite humid, and Meerkat in desert, so it's quite hot and dry. So we use the water, and the fire is in global cluster science and projects. I'm really enjoying the journey of studying pulsars, not just in globular cluster, and excited about the chance to explore a new collaboration with all of you here today. Thank you.
Questions? We have a microphone up front, which I can also maybe.
Maybe a simple question, but maybe if you know the answer. Between using the different facilities and the data that's being produced, have you found a certain data set to be easier to work with than others, or are they all equally?
This is a good question. From my experience, I use PAX data, FAST data, and the Meerkat data. All those kinds of data, if on pulsar mode, it's largely the same. It's basically the same data format, and but will have a little bit different, Meerkat. We need to do some data reduction before we analyze the data for science. So different telescope has a different pipeline to the data reduction. But don't need to worry about that. After we got the data as already done the data reduction is quite thin. Yeah.
Hi, Ronnie is here. Thank you. Because there's a lot of similarity between pulsars and fast radio bursts, for example, the polarization, the genesis may be related. I was just thinking as you were talking, fast would be very good at looking for FRBs in globular clusters. Are you doing that?
Yeah, that's a excellent question. Nowadays, it is true for the pulsar search model data. We can simultaneously search pulsar and also single pulse like FRB-RASC. So now we process all our new data use 3 search pipeline. One is the traditional FFT pipeline to try this sensitivity to the short period of pulsar, particularly in battery system, is based on Presto. Another one is FFA, fast folding algorithm. Yeah, this pipeline is sensitive to the longer period pulsars, like a second period or more. And so because recently we found some second level pulsars in globular cluster. Before that, most pulsars in globular cluster is quite fast, like a millisecond pulsar. So yeah, this is the second pipeline. Also, we use handle or the single pulse search pipeline in which under the Presto search the single pulse. Normally we search the data, the DM range 0 to 5,000. Yeah, if we want to explore large DM series, we need a very efficient pipeline. So we use handle to explore large DM range and use the Presto single pulse search pipeline and do the small DM range explore, because a Presto single pulse pipeline is more efficient to the small range DM changes. Summary is we use we also do the single pulse search for the data.
Great, thanks, Steve. Thanks again.
And then we can move on to Giovanni.
Good morning, everyone. Thank you for joining this session. I'm Giovanni Naldi. I work at the Italian National Institute for Astrophysics, and in this talk, I will present you the design of a new digital signal processing system for the upgraded Northern Cross radio telescope. After a short introduction on the telescope and on the related activities, I will present you the next generation Croce del Nord project with the fully upgrade of the east-west arm, and also the construction of a new digital signal processing system. Then I will focus on the digital infrastructure and mainly on the two hardware components, the FPGA boards and the new high-performance computing cluster. And then I will also mention the planned activities on firmware software development and then conclusions. So the Northern Cross Radio Telescope is located in Medicina, about 30 kilometers far from Bologna, northern part of Italy. It is a T-shaped radio interferometer composed of 2 main arms. The east-west arm is a single offset cylindrical parabolic antenna, more than 500 meters long and 30 meters wide, while the north-south arm is composed on 64 cylinders with a parabolic reflector. And this telescope is a transient instrument. It can only be moved in declination. It works at a frequency of 408 megahertz with a bandwidth of 16 megahertz. It works only in single linear polarization, and as you can see, the mirror is composed on steel wires with a spacing of 2 centimeters. And at this frequency, this mirror behaves like a solid surface. Recently, 16 cylinders out of 64, so a quarter of the north-south arm, has been refurbished and currently are operational. The focal line has been modified in order to group the signals from the signal of 16 dipoles together in order to form 4 receiving elements per cylinder. As you can see, the sensor is a alpha wave dipole. There is a front-end box installed on top of the focal line with the low noise amplifier and filtering a optical transmitter. Then the data are transmitted with through the optical fiber links to the data center room. The upgrade of other cylinders is almost completed. Now let's talk about the main application of this instrument. The first one regards the observation, the monitoring of space debris that are orbiting objects in low Earth orbit, mainly fragments from collisions, spent satellites, rocket bodies, and so on. And the Northern Cross in particular is the receiving element of a bistatic radar. Basically, there is a transmitting antenna located in the Sardinia island in Italy. And when the 2 instruments look at the same sky direction, it is possible to receive the echo radar. The Northern Cross in particular is able to form multiple beams inside the field of view. When the object crosses the field of view of the instrument, looking at the illuminated beams inside the field of view, it is possible to reconstruct and to determine the orbit of the object. The other main project of the Northern Cross regards the research related to fast radio burst. Recently, the Northern Cross has demonstrated the capability of study and detect such a phenomenon. And the project started in 2018. The first light was seen in 2020. Up to now, more than 2,000 hours has been observed, and 70 papers included the Northern Cross data with the works of some PhD students. And nowadays, the Northern Cross is recognized among the instruments all around the world, able to monitoring the most active FRB repeaters and to contribute for many multi-wavelength campaigns for FRB search campaigns. Unfortunately, due to the serious mechanical issues and to the high cost of maintenance, the east-west antenna operation was stopped in 2012. Recently, with the European Union funding, the European Union allocated about 19 million euros for the next generation Croce del Nord project. That includes extraordinary maintenance for the fully refurbishment of the east-west arm. And it includes the infrastructure consolidation, the installation of new mechanical movement system, the substitution of the focal line, installation of new receivers, and optical fiber links. As you can see, the work is in progress. The work to substitute the old focal line has already started. Just a few words about the current focal line. As you can see from this image, you can see the the dipoles are installed in this structure with metallic cavities and symmetrization element. There is also a corner reflector that better illuminates the primary mirror in order to have to reduce the level of side lobes. This structure, which is quite complex, will be substituted with an array of 416 Yagi-Uda antennas installed in the focal line. And just close to the antenna will be installed also the front-end box with the LNA just close to the antenna. And this installation brings two main improvements. The first one is to have a wider field of view, because in the previous version, 256 dipoles were summed together with an analog beamforming network. And the fact to have a noise amplifier just close to the antenna increased dramatically the sensitivity of the instrument. The other important point, not only this one, but one of the most, is the construction of a new digital signal processing system to handle all the receiving elements of the two arms. In total, about 672 receiving elements. And this system will be composed on FPGA boards with for the digitization and real-time processing on FPGA device, and the high-performance computing cluster with many HPC nodes equipped with GPU cards in order to parallelize the computation, a storage system, and a high-speed network. Let's talk about the FPGA boards. This board is the other analog to digital unit developed for SKA. It is the result of a collaboration between INAF and an Italian company, Sanitas. The project started in 2013, and all the firmware is based on VHDL. This board is capable to handle up to 32 analog inputs. It features 16 dual input analog to digital converter with 14 bits resolution. It has two FPGA Xilinx UltraScale Plus. There are 32 GB of RAM and two transceivers 40 gigabit per second with PSFP interface. The ADU board is part of the so-called ITPM assembly. That is a combination of one ADU board on the left and the two pre-ADU boards that are the analog boards before the digitization, containing all the optical receiver and all the RF electronics for the signal conditioning before digitization. This is one of the first prototype of the ITPM board. It was used for aperture array verification system demonstrator in Western Australia. It is the combination of one ADU board, as you can see on the left, with the gridded thing. And on the right, there are two preview boards, one on the front side and the other one on the back side. And this is the newest version, which is adopted for the massive production of SKA and also chosen for the MG Croce project. Note that 4 TPM are arranged in a subrack. This subrack is managed and controlled by this subrack management board on the central part, which provide and distribute all the RF, the time and frequency reference signals, that is the PPS 10 mega signal, and also provide the power supply distributed to the boards, because on the back side there is also a backplane board. Let's talk about the most important processing block inside the FPGA, starting from the analog to digital conversion with 1 gigasample per second. The band of interest is then down converted with the DG block with a decimation factor of 20. Then there is a time-aligned block in order to compensate the delay difference between antennas. In the center part, there is a transient buffer in order to store the raw antenna data voltages, which is useful when there is a detection in order to reprocess the corresponding data to a detection further. There is a coarse analyzer block based on oversampled polyphase filter bank implementation. Then the data packetized and sent through a 40 gigabit Ethernet interface. As per the HPC cluster, this system is managed and controlled by 3 master nodes, which also act as login nodes for the user who want to operate the system. The data coming from the backend are real-time processed by many HPC nodes equipped with GPU cards in order to parallelize the computation. These nodes also has a distributed RAM buffer in order to have a second level of transient buffer in order to store the raw channelized data coming from the backend, as said before, in order to reprocess if there is some detection, we want to retrieve the corresponding data and reprocess again. All the data are stored in this system, the object storage, and the data can be reprocessed a second time from these nodes that are used for the data post-processing and also for development purposes. Just to note some relevant number about the HPC cluster, every node has 2 NVIDIA L40S GPU, 2 TB of RAM for the distributed memory buffer. The SSD disks are used to transfer data from the RAM memory to the object storage, and NIC cards for the data acquisition. Another quite relevant number is 8 PB of total disk space. All the system is housed in this infrastructure. Note that it is a building inside the data receiver room. It is all air-cooled by 4 air conditioning units. There are 2 rows of racks, UPS for the data continuity, for the electrical continuity. Just to mention the most relevant real-time software operation. Data coming from the FPGA boards are distributed through a multicast network switch to the HPC nodes. After data reception and buffering, data are transferred through GPU cards in order to perform multi-beaming here and cross-correlation among antennas. Cross-correlation serves in order to calculate the calibration coefficients, in order to calculate correctly the beams. Once the beams are formed, they are passed to the 2 real-time pipelines, the FRB1 and the space debris. The FRB pipeline is the most computational intensive since it processes all the bandwidth at the same time. And also there are critical operations like the dispersion and matched filtering, while the space debris pipeline is less critical because it processes only a small portion of the bandwidth. Conclusion, we have seen that thanks to European funding, the entire Northern Cross is undergoing a great upgrade with the complete refurbishment of the east-west arm. The upgraded Northern Cross will be equipped with a new digital acquisition and signal processing system. There are considerable work for firmware and software development for real-time operation. And with this project, we expect a significant improvement, both for space debris activities and FRB research. Thank you.
Thank you, Giovanni. That was very cool. Congratulations. It seems like it's a combat amount of work, very stressful, I imagine. I wanted to follow up on the HPC nodes that you guys had, 18 nodes.
Yes.
Plus, not the most number, but it seems to pack quite a lot of processing power there.
Yeah.
Were the nodes designed, like the composition, the CPU, GPU combination?
Yes.
Did you decide on that within your team, or
yes, we have tried to make a balance between computation and, for example, RAM memory and other kind of, and also to balance with HPC nodes and storage nodes. So we have tried to find the best balance. At the moment, honestly, we don't know if this computing power is sufficient because we don't have a real benchmarking system already in place. So it is difficult to establish if the computing power is sufficient now. We will see as the process, the project progress. And this system is scalable for the architecture. So in case we recognize that it is not sufficient, we can scale up because it is quite easy to add some other nodes in order to distribute the frequency channels and parallelize the computation. So it is quite scalable. Okay.
If I can ask one more, you said it's a dual CPU configuration you have. You'd like to say which brand of CPUs you have?
I don't remember that, but I can. Okay.
Any other? Yeah.
Very interesting work. Yeah, this something. So you have a very powerful backend, but is the bandwidth still limited to 16 megahertz?
Yes, it is a limitation for the instrument. We have a massive number of receiver at the same time, but a small bandwidth, I know, but and only single polarization.
Okay. 4 megahertz is the tinian bandwidth, so around similar frequency. So if it is to image search, I wonder for 16 megahertz, it's kind of a marginal. I wonder whether you still need dispersion measure search or just form the image.
Yeah, maybe yes.
Yeah.
Maybe I hope it was loud enough.
So,
Okay, interesting. I watched the ITPM before the beginning, so I guess I actually see the board.
Yeah.
But these days, there are chips that do the whole thing that we have on the ITPM on one chip, the RF stop chip. So, is there any work about updating or future or anything like that?
Well, we are using mostly ITPM because we have experience for the SKA project. So the selection of the boards was quite easy because we have we are reusing most of the firmware developed for SKA. So we are quite happy up to now with these boards. We have experience. We know the performance. So for the moment, we are mostly focused on this backend.
Yeah, thanks. The 16 channels on the FPGA are completely independent, right? So you have some amount of resources, like 32 gigs of RAM on the board, and then you're down converting, channelizing, etc. Can you down convert less and use less channels, considering they're all independent? You have like a 1 to 50 down conversion or something, right?
Yeah.
So could you?
Yeah, in principle, yes. Yeah. We can select the bandwidth changing parameters on the chip inside. So yes, we can select all the bandwidth we want to. Sorry.
Or not?
In principle, we can process more bandwidth. Yes. Yeah. Because the ADC goes up to 1 gigasample per second. The analog digital conversion could be upper. So in principle, yes.
You only say that you love that.
So next up is Ronikas.
So good morning, everyone. Good morning, URSI attendees. Coming here on the train this morning, I realized it's more than 50 years since I gave my first talk at an URSI meeting. And so I reflected a bit. Not much change, but of course, that's not altogether positive. So you might think about that. We can now record things, which is why I make a fuss of people actually using the microphone instead of thinking you're just in a small face-to-face meeting. All right, so off topic already. That's typical for me. I'm giving this talk on behalf of Ray Lowe. I can look from here, right. Who worked with me on this topic when he was a postdoc in CSIRO some years ago. But as you will discover, and as Ray may find out, I've changed quite a bit as we go through this. Assuming I can use the keyboard. I thought I would give a little historical context, and this is partly triggered by Lewis's comment that there's a history of the SKA already written, and I was one of the co-authors. So I just thought I would put this in context, the idea of beamforming arrays, pointing out that quite early in the SKA process, the multi-beam concept became very important. This was one of the very early diagrams, actually, from the SKA, various SKA working groups. Interestingly, even though things like the Northern Cross, the Mills Cross had been doing beamforming for decades, all of a sudden, this became much more broadly recognized as a huge advantage that radio astronomy has. That is, you can divide up radio signals into multiple beams without losing signal to noise. In case you haven't thought about it, the other side of the peak in the Planck distribution, that is not possible. An optical interferometer cannot play this game. So we have this huge advantage, and we should capitalize it. So there was a strong feeling early in the SKA that providing a wide field of view with multiple beams would enable multiple users to use the same telescope at the same time. And this was, and the real difference is the technology to achieve this was just becoming possible in this period. So it actually had a big influence. As David Davidson pointed out in his general lecture, this becomes possible when you have arrays. And it is not so easily possible with dishes. And in the case of arrays, you then have to decide what's the case for having a dense array versus a sparse array. As I go through this talk, I am really going to push the concept of the advantage of dense arrays, and in particular for transient radio astronomy, where they can make a huge advantage because you can instantaneously have a very large field of view with a dense array. And as I will point out as I go through with this, with sparse arrays, getting instantaneous coverage of all the possible beams becomes a computing nightmare, becoming nearly impossible. Rather sadly, this is coincident with the session J05 on time domain astronomy, because the real science case for what I'm going to talk about is time domain astronomy. As I point out in the bottom section, can I put a cursor on the screen? I can, but you can't see it. Oh well. So much for adopting technology. Time domain, because a transient survey never finishes. This is very different from a survey looking for sources which are there continuously. So if you want to discover a new transient, that's proportional to how much time you spend looking and how much area you're looking at one instant in time. That means the discovery rate is going linear with field of view. That is very different from sensitivity limited surveys where the sources are always there, and the only way you can discover a new one is by having more sensitivity. And that goes as the square root of the field of view in the figures of merit. So warning number one, most figures of merit which are publicized are not done for transient surveys, they're done for continuum surveys. And that puts, whereas there's actually a huge advantage from field of view, and that should be kind of obvious by looking at what's happened as a result of field of view. So a slide here put together by Ray Lowe, showing how field of view plays a critical role. So in the case of the Parkes multi-beam,
that generated this huge spike in pulsar discovery rate when it was installed. Suddenly, PARCS was 13 times better because it had 13 beams there at the same time. Not only that, as you may know by looking at the second diagram, this discovered the first fast radio burst. You might want to think about this, but I put it to you that without the PARCS 13 beam receiver, we would still not be discussing FRBs. I do not believe any other telescope would have found them. So you can think about that. Just possible we would have come across one, but unlikely. The next step here is the effect of ASCAP with its focal plane array. And here, and I'll talk about this maybe in a little bit later, if you want sensitivity and field of view, focal plane arrays are a compromise where you have dishes which are increasing the collecting area, but you're maintaining some of the field of view with a focal plane array. And this shows what happened to the FRB discovery rate when ASCAP appeared. Then CHIME is, of course, another focal plane array. This is a linear array and an incredibly powerful one. I might also remind you, the CHIME design was one of the prototype SKA designs, which was copied by CHIME. They very interestingly decided to specialize and built this beautiful instrument. This is a very large linear array at the focus. So it is another example of a concentrator and has been hugely successful finding transients. So this is all about field of view, guys, not just collecting area. Now, the case for going to a dense array is because if you want instantaneous coverage and you're seeing the whole sky, which is what the discovery rate depends on, you need all the beams that cover the field of view, not 10 or 20 or even 100, but the thousands of beams that can then simultaneously see the entire sky. I also observe throughout my entire career, radio astronomy has been limited by the data processing available. You may think this is a new problem, but when I started as director of the VLA, there was a whole range of science we couldn't do because there wasn't enough compute power. This has actually not changed. The ability of our telescopes to make data has increased with Moore's law. The ability to process it has gone up with Moore's law. It's the same now as it was 50 years ago. Sorry, this is not new. So the science we can do in almost all the FRB search engines is limited by compute capacity. It's limiting the time constant. It's limiting the dispersion measure range that can be searched. So reducing the computer capacity is important. The denser you make your array, the less beams you need to cover the full sky. So it directly impacts the science you can do given a compute limit to what's possible. So if you want a really dense array, again, David mentioned this, but only in passing, connected arrays then become the densest possible solution. I'm showing one example because I thought it was so beautiful when this concept emerged, again, out of engineers working on SKA concepts. Of the checkerboard array, that's a connected array. In that picture, each of those little blue things is where there's an amplifier. And it's an amazing array because it is this self-complementary. If you switch the insulating and conducting segments of that array, you get exactly the same array. Babinet's principle then applies, and you have a free space impedance with no frequency dependence. Just compare that with our SK low antennas and think of the difference in complexity of these two solutions. Well, because of the power of all sky monitors with these compact arrays, there's actually been a lot of development. And if you want a quick overview, which I don't have time for, and this slide which was prepared a year or so ago, is already out of date. Look at Science News last month, and there's a very nice review featuring Adeli's comments, among others, on the telescopes which are being built. On the left, we have the Galactic Radio Explorer T-REX, triggered by Caltech, and the realization that field of view is so important that even a single element could discover something new. It found the galactic magnetar. That is a game changer with one element. So amazing. So that is now leading to new developments, joint Caltech-Harvard, which isn't on Ray's slide because it's more recent, funded, I think, by the Schmidt Foundation. Whaley Penn has always been a strong proponent of this kind of all-sky monitor and finding the rare transients. The rare ones are going to include the small fraction, which are very useful for all kinds of science. So here's the burst array, which is now beginning to operate in Taiwan. The next one shows an example of doing an all-sky monitor with an SKA prototype low station. So there's a lot going on. Now, the reason this talk is in the form it is, and that Ray Lowe was going to give it, relates to the fact that we were developing a cryogenically cooled phased array for the Parkes telescope. That, by the way, is being, I didn't add it to my slide. Simon Johnston will present this on Thursday in Session J07. It is a very good receiver, as you can see in the central plot. The bottom line is the one you look at. That's what we usually quote. It's the system temperature, and it is below 15 degrees over quite a nice wide band. So this is really a very powerful array. The fact it's a focal plane array, some people imagine, oh, you can't get good system temperature with a focal plane array. Well, the engineers have solved that problem. You can do a connected array and achieve this kind of performance. The other plots are divided by efficiency, which is another way of looking at it. So the parameters of this particular array are there on the right. But what I said to Ray Lowe was, what would happen if we took that receiver and instead of putting it at the focus of a 64-meter telescope, we take it out and put it on the ground? And he had simulation software for simulating a universe of FRBs. So it was very easy then to simulate what you would see with it sitting on the ground compared with what you would see with it on the focus of the telescope. And the next slides are all done by Ray and show the difference. We put it on the ground, we can form 72 simultaneous beams. They are all monitoring a quarter of a hemisphere all the time. So plug that into his system. And I forgot to introduce this slide. All right, I'll keep the order the same. I'll get back to his simulation in a second. Just finding an FRB is really useful, but as we quickly learned on ASCAP and as others have learned from the repeaters, localizing them is really key to doing the science, and just finding them, even if rare by itself without a position, is not good. But for these transients, a transient source is by definition a point source. And if you take a difference in an image with it and without it, there's a single point source in the image. This is dead easy to position. You need three antennas only. This, of course, is the way that CHIME is positioning FRBs. It did not need a lot of other stations because it can solve the position with 3 antennas. And so Ray Lowe, who is now in China, imagined doing this. All right, Ray Lowe took his simulation software, which is described here. He had already used the luminosity function of FRBs. You can combine that with the redshift distribution with the distribution of the width of the pulses and with the host DM in a model, make a universe, which is what he makes then in the middle plot. Oh, sorry, the pointer is again not working. He produces all the FRBs in the sky. Then in the red box is the really important step, which Ray did very carefully, and that he applies the actual survey selection which current telescopes apply when they're looking for FRBs. In particular, the DM search range, the time constant, which is critical, and because of compute power, many searches are limited to tens or hundreds of milliseconds, not milliseconds. And so he plugs all of that in, and I'll just show you the result of a couple of these simulations. And because we could do this for the same receiver, both on Parkes and off Parkes, oh dear, we can now compare just two cases for simplicity. He's done many others, but I'll show you these two. So on the left, the red shows you where the FRBs that are found in this survey are with Parkes, and the blue is where they're found with just the focal plane array on the ground. So obviously the dispersion measure on the x-axis, these are going to be much closer because we have very much lower sensitivity, but because of the huge field of view, we still find a large number. A rate of a few per week, which is actually about the same as Parkes will achieve when the cryopath is working on the telescope. But it samples different parameter space, and that is how we progress in science. By comparison, more sensitivity pushes you down in the other direction, so these are all complementary. But they're not replacing. A high-sensitive telescope does not replace a low-sensitivity wide field of view telescope. And on the right-hand diagram, what it sees are the blue ones. Because the sensitivity is so low, it can only see FRBs if they are really bright. And the really bright ones are really rare, and you find them with this huge field of view. This field of view is hundreds of times any previous field of view. So I think there is a really strong science case. We can look at other science cases, and in 2 minutes, this is just going to be really fast. It was realized that the gravitational wave, detecting gravitational waves is a nearby universe study, and it is very well matched to the range of distances covered by this. And you find a gravitational wave, you would like to know, was there any electromagnetic interaction which occurred when that binary merged? But you need an observation at the same time, not months later, or even days later, or weeks later. If you've got an all-sky monitor running, you've already observed where the gravity wave came from. So I think this has got amazing potential. I was really amazed when I asked the question to some of the magnetar experts, what is the number of radio magnetars in the galaxy? Answer, we don't know. Nobody's done a galactic plane survey. I found that almost unbelievable. So we do one. Long time ago, speaking of now quite different things, I have a reason for introducing it. I'm going to go a minute over, sorry. The case, there is a SETI case called the omnidirectional SETI system, and it's really the third on strategy for SETI. If you are trying to be detected, it is by far your best strategy to pack all your energy into a single pulse, which can get above the receiver's threshold, and you would target somebody. But if you're receiving, if you're transmitting, you can't transmit into multiple beams because you don't have enough energy. You put all the energy into one beam. If you're receiving, it's not reciprocal. You have all the beams all the time. So an all-sky monitor is perfect for SETI. We proposed putting one to the Breakthrough Foundation on the far side of the moon to get rid of all the RFI. But that triggered something which I do want to get to my last slides. Namely, if you're on the far side of the moon, you've got a little bit of trouble powering a wide bandwidth, high-speed digital beamformer. So we asked our engineers to come up with an alternative. And Paul Roberts went back in the literature and said, hey, there's a thing called a Rotman microwave lens, and it can do an analog beamforming. And here it set out how to do it. These devices were already understood even in the 80s, but digital computers killed this technology. So Paul has gone and built a version of the thing on the top right, which is one-dimensional. If you read the rest of this, which you already have, I hope, you can turn it into a two-dimensional array just by stacking them. Here's the one that Paul built, and here's Paul Roberts. Paul couldn't give his talk at this meeting because he has a family medical crisis he's attending to. So he asked me to include this slide, so I'm sorry about taking another minute of the time. This thing down there takes 8 inputs, which you see on the left-hand side. The delays across that dielectric exactly compensate for the delays if you're forming beams. Out the other side come 8 beams. And the amazing thing is it takes no power, and it is time delay, not phase delay, so it's full bandwidth. So this thing has got a gigahertz of bandwidth. The actual measured, not the simulated response, is on the left, and it's brilliant. And if you think about it, when you beamform in the image plane like this, you don't need the extraordinary dynamic range requirements of synthesis where you're interpolating all the missing spacings. All the spacings are present in this. So this, about 2% accuracy, is absolutely adequate for radio astronomy and can work at a gigahertz.
Thanks, Ron. That reminds me of a previous life in the electronic government. We have time for one quick question. Otherwise, I think if there's no burning questions, I think we should move on in the interest of time. Thank you again, Ron.
So next up is Pedro. It's Pedro. Oh dear. I just have questions for someone who's missing.
Ask one question.
Yeah, so since our speaker is missing, let's carry on with the question.
So Ron, so the analog beamformer, is that what's the constraint on the bandwidth?
No constraint. One of the other advantages is you have your antenna. The LNA feeds into this beamformer, so you've amplified the signal, so the losses in that beamformer are taken care of. The one I showed you has a gigahertz of bandwidth. The constraint comes from the physics of the delays. So if you go to a sparse array, this becomes almost immediately impractical. Going to high frequencies isn't a problem, but this means you can't go much below about half a gig or about 0.7 gigahertz. But the one I showed you is 0.7 to 1.7. That would take kilowatts of digital signal processing, as you probably know.
Yeah, whatever. Oh, sorry, give the microphone down. I'll make sure I talk into this. So you have 8 inputs out, 8 inputs, 8 inputs, 8 outputs, but there are also a series of estimate ports on the far side. What are the other 2 sides doing there?
The other 2 sides are matching.
Any other questions? Does anyone have a way of contacting Pedro? Okay, they're looking outside. And I think if it does not show up, then we will wait until the next time slot for continuing. So it'll be a quick demonstration. All right, let's go with that. Thanks again, Ron.
Learned a bit about how the other position. You're definitely the property. How do you know they're there? You're saying, you know, the activity, your right stuff. I have a most function. Yeah. Okay, so it is the backlinks. Yeah. Okay.
So it's like saying, but now you can ask, we know it's activity, on the right on the front, we have.
Yeah. So it is, it's looking at some part of the sky over time, you know, there was just any bright one. Okay.
Yeah, I have done this. The first and only actually from a management one. So you will have to be flagged out by most of the telephone. Right. And so immediately after that event, there are a series of models showing that in the spiral galaxy that delay happens every 5,000 to 10,000. But I didn't leave that because I know that this is the two discovery papers, one by the China, which I agree with international peace. Then there's this single branches to the Chris Roshnik, which I always worry about how these graduates. He done this experiment by himself in 3 years. Yes, he has very rough antennas, but hard and innovation and classical physically and trying to match the current time. So Chris is very good. And can also be very helpful. Like if you tell me there's one event and so you'll be waiting every 1,000 years and it cannot practical 1 PhD. So it's probably happens every year, right? Or at most every.
That's what I was talking about magnetite. Maybe only colors not from one side of high energy.
Yes.
Well, that'd be great.
Exactly. So
it's already
birds that maybe they're not fast breeding birds. There are some birds that, but they're just very close.
By the way, about the array design, which would be often on the open way. On top, we want to optimize the spatial array. Yes,
but in the planning, you should need or something. Sure.
Okay, yeah, so the output of this before now is now a wideband signal. Here's how many things. So put something from the end. We're looking at analog the general comment is problem so predicting my lunch probably
at some point you have to have to take this data as well, it's not really analysis how to.
And that's all.
But they are so busy with usually running where the money is.
Even that's, I mean, that's still pretty, that's because it's still hardware as well, right? You're seeing these massive AI farms that are no longer using computing. This is not, but this much more like, well, hardware like this type of drill. We'll see.
By the way, what's the size of your array?
This is 1 meter, and it's 112. No, 112.
Oh, so that, the thing we were ready to go.
Yeah.
From there, with the formation is paper, and you launch it there's practical limitations on paper link. Everybody sits down, that's another. Yeah.
At the high end, I guess, you can't get the same line, exactly, yeah, okay. Yeah, it's quite cool.
It's beautiful.
But again, one of the things you hear, like, yeah, of course you can do that. Yes, you know, it's not it's a very cool to see. Very cool to see it built as well. Something to have on paper.
So those results, and I just look at those results, but then I also think that's just
Right now, it's on the premises of the last year. The RFO is so hard. I go on the west, we the well, right now, right now, we only right now, it's like one chance.
All right, we're ready to restart. So if everyone can just settle down. I will use the opportunity to again acknowledge CSIRO, who are the sponsors for the session. So much appreciation to them. And so we're moving into a little compact array mini session here, and that's going to be kicked off by Chris.
Thanks. So yes, I'm Chris Phillips. I work at CSIRO and I'm the Big Cat project leader, and I'll get on to explain what Big Cat is in a moment. I'd like to start by acknowledging the Gadigal as the traditional owners of the land we're meeting on today and pay my respects to their elders past and present. So the Australian Telescope Compact Array, ATCA, or the Compact Array, it's an interferometric array of 6 22-metre Cassegrain antennas spread over maximum baseline of 6 kilometres. It's a reconfigurable array with the 5 inner antennas movable over a 6 kilometre track with the shortest configuration is 75 metres up to the 3 kilometres, and there's a 6th antenna on a fixed position that makes a maximum baseline 6 kilometres. It's roughly 400 kilometres northwest of Sydney, and it was opened in September 1988. Since the original digital system, they upgraded the back end to the CAB system. That was approximately 20 years. I forgot to write that down. And that's a 4 gigahertz processed system. It has 2 tunable 2 gigahertz bands over an 8 gigahertz IF that comes out of the receivers. And it's worth noting, unfortunately, when that was installed for VLBI, we still only retained 2 times 64 megahertz VLBI. And I should have mentioned also, the system runs from 1 gigahertz up to 105 gigahertz. So it's a very wide frequency coverage with 5 separate receivers. So the Big Cat upgrade is an upgrade of the digital backend. So it's the broadband integrated GPU correlator for the ATCA. And it's a complete replacement from all of the digitizers, all of the correlated backend, and the last stage of the down conversion, the IF. And it uses a hybrid FPGA GPU backend. FPGAs are the digitizers and GPUs for all the sort of cross-correlation processing. It's partially funded by Australian government LEAF grant. It was led by Western Sydney University with Ray Norris as the PI. The key aspects are we're doubling the instantaneous process bandwidth, so processing the full 8 gigahertz. I mean, I think it's technically 7.8 gigahertz. It's be a much more flexible system because the back end is completely software defined. So much more flexible spectral resolution, which is one of the main problems with the CAB back end. The CAB reliability has been problematic in the last sort of few years, so it'll be much more reliable system. Much more flexibility so with the spectral setup as well as integration times. We can go down to very short integration times if we wish. And also the system is designed to very rapidly change between observing modes. The current system, the observer has to spend quite a while setting up new correlating configuration. Some of the spectral line setups were taking up to an hour for an expert observer to set up. This new system will be sort of tens of seconds to change between completely different setup modes. So for things like rapid follow-up for target opportunity things, this should be a much more flexible system. And the plan is to retain all of the features such as the mosaicing that the CAB backend retained, as well as adding new features. So the basic setup is the existing antenna infrastructure, the receivers and so on are not changed. As I say, the existing receivers have an 8 gigahertz IF output, so we're sort of tapping into that. So there's a new section where we're replacing the last stage of the down conversion with a new sort of system that takes 8 gigahertz RF in or IF in and breaks it up into 4 2 gigahertz chunks. These are partially tunable, but very limited tuning. They can only tune sort of plus or minus 500 megahertz in 160 megahertz chunks, but because it's covering the full range, this doesn't matter. This then goes into a new digitizer, a custom-built system, the gimbal. John Tutter will be talking about that in the next talk. But the main thing about that is it takes the signal, it channelizes it into chunks of 128 megahertz and transports it to the GPU over 100 gig Ethernet. So it's complete COTS. Once it comes out of the RF sock, we use completely off-the-shelf systems. The data from all the antennas goes into a standard Ethernet switch. It's a Cisco switch, nothing special. Then we have a cluster of GPU servers. So we have eight servers, each with 2 GPUs in them each. So I'll very quickly go this. John's going to talk this in detail, but the main issue is so that it channelizes the data and sends out UDP multicast data over Ethernet to receive the rest of the system. The input data is 14 bits. After channelization, we generate either 8 or 16 bits. When we're doing the full 8 gigahertz bandwidth, the network connectivity, the fibers we have, only allow us to send 8 bit data just because of the available network bandwidth we have accessible to us. For the GPU backend, as I said, we have 8 servers plus 1 hot spare. Hot spare is in case obviously of a system failure, but also allows us to do parallel testing and development during operational usage. Each as a dual processor system, 2 dual port 100 gig Ethernet cards, and we're using the NVIDIA L40 GPU. So this is the same architecture, the Ada Lovelace architecture as the gaming RTX 4080. So we're certainly when we bought these 18 months ago, sort of the newest generation of the NVIDIA cards. And we're processing 116 gigabits per second per GPU. So it's a lot of data throughput. We process each 128 megahertz coarse frequency channel independently. So the idea is from the telescopes, all of the same frequencies go to the same GPU. So we're basically the network switch is using as a cross connect. There's no, on the software perspective, there's no cross connect between those subbands. So which simplifies the coding. Each GPU is processing 4 coarse channels. So sort of in numerology. So each antenna is producing almost 300 gigabits per second. So there's a total data rate of 1.7 terabits per second. So not quite at the same data rates that Lewis was talking about for SKA, but still a huge amount of data that we're processing in real time. So the hardware architecture is quite simple. We have a Mellanox network card that receives the UDP multicast data. And then it transfers the data over the computer PCI bus onto the GPU, it does its processing, and then it's transferred back onto the CPU and then sent off to an ingest machine. From a software perspective, the data coming in goes into a ring buffer on the CPU. Then it's asynchronously copied onto a double buffered system on the GPU. That happens while the previous integration was processed, and then the same process, a double buffer on the GPU, is used to store the data, transfer it off, and we then send the data off to an ingest machine where the data is further integrated and written to disk. We're using the ASDM data format to give the data to the astronomers. In terms of control and monitoring, we've adopted the so-called ZMQ network library. This is a layer that sits on top of standard Unix sockets. One of the nice things that has many advanced features, such as the concept of broadcast. So the main control software can send a broadcast message out. All of the GPUs receive the same message, and then they do the appropriate processing. So this is really simple, has simplified our control system. Control message is simple JSON text messages. That works really well. Obviously, JSON is not very good for transporting the visibility data. So then we have sort of binary blobs that go over the ZMQ messages. This has worked very well, and we have a very, very simple control layer. And for me, that's very good, because the simpler you can make it, the more reliable it's going to be. I should more, as I said, the raw data comes in a telescope, so it's just CODIF data over UDP. CODIF is a variant of the standard VLBI VDIF format. VDIF was not suitable for the data rates we coming from the telescope. And when we're running in VLBI mode, we'll resample the data and generate VDIF data over UDP to go to a VLBI data recorder. Partially because of memory limits on the GPUs, we process the data in very small subints, typically a few hundred milliseconds. But because of the flexibility of doing this, we can actually grab the data at these very short subints, and that's actually proved very useful for commissioning and testing. We've discovered a number of existing problems with the antennas, nothing to do with a big upgrade, phase stability with some of the systems that you only ever see when you start looking at the data at very short integration times. The previous CAB system had 10-second integration times and actually was just averaging over some subtle phase effects on the system, which we've now fixed. So we're really sort of finding a number of issues because we've sort of changed the parameter space. In terms of commissioning, we installed the big cat digitizers on the antenna in April this year. There's been a lot of engineering commissioning, getting things going. We did start science commissioning 2 weeks ago, which has been really pleasing to finally start seeing. In terms of testing, we've done a lot of extensive comparisons with the existing CAB system. We could run some big cat and CAB tests in parallel. This plot on the lower left is the phase plot of the data coming from CAB and CAB and big cat at the same time. You can't really see any difference because that's the phases are lying on each other perfectly well. So that's really pleasing that we're still getting the same result. We've also used the DiffX VLBI software correlator as sort of ground truth. And again, we're getting results basically identical to the DiffX software correlator. In terms of, these are some results from just the last week. So we are now getting some nice images from the system, which is really pleasing. So this top left is I've written it down here. It's a galaxy, so you can see we're getting sort of nice images. Top right, which I quite like, is 2 radio stars. And if you can see the blue circles, that's the position of the optical source. So you can see we are actually getting positions where you expect, right, exactly where we are. And this other one is a gamma ray burst, and I think that's the particular source of interest. And the flux measured is exactly where you'd expect on the current light curve, which is very nice. In terms of timelines, as I said, we installed the digitizers in April, started commissioning. Currently, we're still running with the old CAB IF, so the 2 times 2 gigahertz. That will be running with that until November. So we're planning on starting sort of shared risk scheduled observing from mid-October. There's quite a bit of delay from now till then. Unfortunately, in terms of timing, completely unrelated to Big Cat, there's a infrastructure upgrade of the antennas themselves. So there'll be a 6-week shut down from the 1st of September. That's just coincidentally ended up running into each other. So we're very much in the middle of the moment of manufacturing all of the IF equipment, and there's a lot of modules to be built. And the plan at the moment is to install those in the system probably late November, depending on how quickly that process goes. There's been a few delays of things like some of the connectors for the IF connectors. There's a 6-month delay on them arriving, so it sort of pushed some of the timelines down quite badly. Given the time, I'm going to skip over these last two. So one comment to make is that all of the processing code on the GPUs is done using CUDA. All of the algorithms are VLBI compliant. In fact, all of the testing was originally done on VLBI baseline, so we've made sure that we're not making sort of short baseline assumptions. And the kernels are written in an independent library from the main Big Cat code. And once it's tested and documented, we'll be releasing this under a GPL v3 license and making it available for anyone who's interested in this sort of interferometric processing. One-off issue, though, of course, is that the kernels we've written are very specific to what we need for the compact array. And as an example, we only have unpackers for 8 or 16-bit complex voltages. For instance, for VLBI, it's typically 2 bits, but they would be relatively easy to add if someone was interested. And we're more than happy to make this available for anyone who's interested. If you want some more information, so I said, I'm the project leader. Elizabeth Mahoney, she's here or not? Hello. She's the project scientist. If you've got questions about the science commissioning, talk to Liz. And Jamie Stevens is based at Narrabri and is the compact array senior systems scientist. So more general questions about the telescope, please contact Jamie. Thank you.
Questions? Thank you very much for that. And congratulations on making it a really big upgrade.
Yes.
I'm sure that was stressful. Let's just say, surprised at the amount of compute that people have decided to pack into their nodes, at times 2 in your case with the GPUs.
Yeah.
Considering our experience at Zereo in developing our HPC nodes, let me call it a bold decision to put 2 GPUs and try to do things simultaneously. Did you find that development process relatively seamless, or?
It depends which aspect you're talking about. So concerns like this, the raw computing, heat load and so on, that's no problems. We've got Dell servers that are designed to have these sorts of setups. Certainly our part systems have 4 GPUs each server. A mistake that I made is I think the CPUs we have, the memory bandwidth or speed is slightly slower than we should have gone for in hindsight. So we're pretty much close to the hairy edge. So we were having some issues, and it's the data rate. So the GPU stuff is fine, going from the network card to the GPU without doing anything funky. There's all sorts of DMA type things you can do, but I was trying to avoid very complex network dependencies because I think it just makes it harder longer term. We'd do it if we have to. We ended up having to use Mellanox. We have to use the VMA libraries for Mellanox. I had to use some very poorly documented zero-copy library calls. It's only a few lines of code change, but then it means it is no longer standard networking, but it is only a few lines to get that going. But yes, that for a few months we had a problem with packet loss.
If I can ask one more question, how did you settle on the GPU choice? Did you go through a couple of iterations, or did you just go, we want big, we want types?
There's a few. So one of the issues, obviously we've had some prototypes, and we went through a few generations. We did end up just like buying a gaming GPU and end up whacking at someone's personal computer because it was the only one that we could. But one of the things I found for the code, the throughput was completely dominated by the theoretical memory bandwidth from the GPU. I've got a nice plot, and I've never seen such a slight plot. So the L40s that we ordered, we never tested. and the results came out within a couple of % of the predicted speed. We're completely memory dominated in the compute. So I ended up just going to a list. That's what I can afford, and that's got the speed I need.
Any other questions? We have some time. Yeah.
So how are you trying to avoid the host to device memory transfer or limit the host memory device memory transfers? Are you trying to just transfer one chunk which you're going to integrate? I suppose that's what is also limiting your bandwidth per GPU. That's possible, right?
I mean, look, ultimately you're limited by the bandwidth over the PCI bus and all of that. We're running at roughly 60% of the theoretical bandwidth, or at least of the network card. Our real limitation is the CPU memory bandwidth. And we could improve things by going for much more complex networking libraries. You can transfer the data directly onto the GPU, but the algorithms the approach we take on the GPU, if we did a complete transfer, that was going to get problematic to then remap things. It's much simpler doing the sorting of the packets, which may be missed or come out of order on the CPU. You can do it on the GPU, but again, all of this, as much as possible, I've tried to keep the algorithms and the processing as simple as possible. I'm a strong believer. As soon as you get complex, you make mistakes.
Then you're actually increasing the host to device memory transfer rate, and that limits your processing capability and speed.
Well, it doesn't process. All the processing on the GPU. So once we can get the data into the GPU, then we've got as much processing as we want. So the limitation is going to be if we can't keep up with the data rate. And also, we have a fixed data rate. The data rate's coming from the telescope is fixed, not changing it. So if we get that working, we're sweet. And what the current system works, so we'll be leaving it like that.
Sure, but what I'm saying is, see, it doesn't matter how much compute your GPU has. It's always the memory bandwidth that's supported between the CPU and the host of the device. That's going to limit your processing.
Well, but okay, I know what I'm saying. It doesn't limit us because we're going fast enough what we need. Therefore, it's no longer a limit. So there's be absolutely no point trying to optimize something that now is good enough.
I think the confusion there is once the data is in the GPU, the limiting factor is the device bandwidth, memory bandwidth on the device. That's the memory limit that he was running up against.
Sorry. Yes, exactly.
So basically, but once you measure that and then the predicted value, the data sheet value of memory bandwidth tells you the processing rate that you can achieve.
Yeah. But I'll point out we weren't troubled by that. That just is the limit. I mean, these GPUs are for standard processing are more than fast enough. We have plenty of compute available. If and when we try and get onto real-time RFI detection, we may be struggling for compute, but until we do that sort of thing, the standard processing, we have no issue at all with GPU compute.
Thanks again.
Right, and so sticking with the same instrument, over to John.
Thank you. Morning, everyone. Chris has given a nice overview of the Big Cat system and the current operational state. So I'm going to dive a bit deeper into the digital receiver or the single chip wideband digital receiver that is part of that Big Cat upgrade. So I begin by acknowledging the Gadigal people of the Aurora Nation as the traditional owners of the land and the coastal waters that I'm presenting from today, and I pay my respect to elders past and present, and extend this to any of First Nations people present here today. I'd also like to acknowledge the team, so Mia, Daniel, Sam, Paul, Grant,
Chris and Peter, who've done an enormous amount of work towards getting this to the state that Chris has shown in his slides. And some of the folks are here in the audience today. So I won't go into what Big Cat is. So I think Chris has already provided an overview of that. So just diving deeper into the architecture of the back end at the antenna. So this is a per antenna architecture diagram. So you can see the IFs from the antenna and the receiver conversion system come in on the left-hand side there, the two polarizations. They go through two 8 gigahertz bandpass filters and then are split 4 ways. And again, a second set of IFs and 2 gigahertz bandpass filters provide 4 2 gigahertz bands for both polarizations that are then fed directly into the inputs of the two gimbal digital receiver cards. And I'll show what those cards are in a moment. So inside the gimbal digital receivers, the 2 gigahertz of bandwidth is channelized into 128 megahertz oversampled channels. And then they're transported back to the central correlator room over optical fiber at 100 gigabit Ethernet or using 100 gigabit Ethernet streams. Oh no. Batteries come out, sorry. There we go. So the gimbal is one of a couple of jellyfish themed hardware platforms that we have at CSIRO. So gimbals are, if you're not familiar, it's a box jellyfish that inhabits the coastal waters of Australia. It's a close relative of the irukandji, which is a much more dangerous version of it. The gimbal digital receiver, though, is based on a single AMD Xilinx chip. It has an analog bandwidth of 6 gigahertz. We process 2 gigahertz of bandwidth. It has 8 RF inputs that are simultaneously sampled at 4096 megahertz and at 14 bits of resolution. It has 2 100 gigabit Ethernet optical outputs that transport the data back to the correlator room. There are 3 actually available. You can see from the card cage in the photo on the right. Actually, if you want to see a real version of this, you can see the stand outside. We have a couple of gimbal receivers you can look at in real life. The gimbal is a Eurocard standard form factor and around about 70 watts per card power dissipation. Just looking more deeply at the RF system on chip, I'm not sure if you're familiar with these devices. They've been around for a few years now, but they're still amazingly powerful for radio astronomy applications in particular. So on a single die, they have a set of analog to digital converter tiles and digital to analog converter tiles, which we don't use. There's a large and flexible programmable logic fabric, the FPGA. Has a lot of digital I/O as well as high-speed transceivers, which we use for the 100 gig Ethernet interface. It also has a number of quite capable ARM processors, which we don't use at all, except for the initial startup phase of the hardware platform. So surrounding the RF SOC are the analog inputs on the top left there. You can see in blue. So they're single-ended inputs, and they consist of a fixed gain block, a fixed attenuator, and then a single-ended to differential converter before they feed into the RF SOC chip. On the right-hand side, the channelized packetized data comes out on the 100 gig Ethernet interfaces as optical transport. There's also a fourth QSFP optical transceiver you can see on the left-hand side below the analog inputs. And we use that for the monitoring and control of the card, as well as providing the station reference sample clock and pulse per second signal. The gimbal receiver also has the capability of accepting those signals as electrical signals, which has been very handy in the lab for testing. I guess a critical part of the digital receiver is the clocking architecture. You can see that in the bottom left. It's based on a Texas Instruments chipset, so the ultra-low phase noise clock jitter and cleaner accepts the station reference and generates a very clean system clock for the samplers on the gimbal card. And then two RF synthesizers generate the final sample clock inputs into the RF SOC device. On the right-hand side, there's a PROM that we can store up to 8 separate FPGA images that can be swapped in and out very quickly. There are two general clock sources for the Ethernet and the processor, as well as the necessary power supplies. So power is supplied through a standard ERNI connector. One of the most critical parts of the design of the gimbal platform was in the selection of the voltage-controlled crystal oscillator. And from lab testing, it was found that not just the datasheet sample clock or the datasheet clock jitter and phase noise was important, but we also needed to consider the vibration effects, so microphonic noise caused by cooling fans and that sort of thing. That actually had a big impact on the coupled noise into the output sample stream. So we settled on the Crystec device there. You can see highlighted in yellow as providing the best compromise between those two. So the reference clock and the timing synchronization, of course, are the heart of a multi-channel synchronous sampling receiver, and particularly so for a synthesis telescope. The process is quite complicated, but at a high level, there are 3 steps. So we initially synchronize the hardware on the board. So the sample clock references across all of the gimbal boards. Once that's done, the ADCs themselves are synchronized together so that they're all in phase and providing output samples synchronously. And the final step is then starting the DSP signal chain off, so taking it out of reset so that all of the filter banks start on the same instant across the array. And also providing time stamping and synchronization of the output streams. Looking at the FPGA firmware, the primary signal path is through the center in black. So we have a 4 from 8 select. We process 4 of the 8 RF inputs. Those 4 sample streams pass into 2 dual channel oversampled polyphase filter banks, which channelize down to 128 megahertz channels. And they then pass into a dynamic range control unit, which reduces the bit width from, I think it's 38 bits down to 8 or 16 bits, depending on the selection for the astronomy case. That's then passed into the packetizer and 100 gig Ethernet cores for transport back to the switch and the central correlator. A critical part of the whole system, though, is the software and control subsystem that's shown in blue. That's responsible for, well, I think I've got another slide on what that does. So I'll just also point out that the auxiliary blocks that are shown in orange are also an important part of the whole system. So they provide the ability to capture raw samples from the ADC sample stream. You can look at the subband statistics as they come out of the filter bank. And there's also an integrating spectrometer that's built into the FPGA firmware, so you can look at integrated power spectrum in real time. The FPGA build was reasonably full. It's about 3/4 of the logic use and about half of the DSP and memory on the device. And these are big devices, so there's a lot of stuff in there. We still didn't have any trouble with timing closure. We meet timing reasonably comfortably, which is a relief for FPGAs. On the right-hand side, you can see a colorized floor plan of where the major blocks are for the filter banks and the streaming subsystem. The polyphase filter bank has a prototype filter length of 576 taps. It's a fractionally oversampled filter bank, 32/27 oversampling ratio. It has a stop band attenuation of better than 80 dB and a passband ripple of less than 0.2 of a dB. You can see those characteristics in the frequency domain plot there. So the streaming data interface consists of two 100 gigabit Ethernet interfaces. It's the data's encapsulated in a CODIF frame and then transported via UDP and Ethernet. CODIF, as Chris mentioned in his slides, is a CSIRO oversampled data interchange format. That's what the acronym is. It was originally an extension from the VDIF standard to support the fractionally oversampled time series. CODIF has a 864-bit word header that allows you to put timing information, source information, and the data payload details. And the data array payload itself has a user-defined length, so that's typically constrained by network factors like the MTU size. So the software monitoring and control is mostly Python-based with some Rust components for things that need to run fast. As Chris mentioned, it uses the open source 0MQ messaging library. It controls the initialization and synchronization process at the start of an observation. It can continuously control a dynamic range module for streaming output. It's also responsible for configuring starting and stopping the 100 gig streams, and also provides precisely timed event subsystem functions that might be used for, say, capturing ADC data or statistics from the filter bank. On the monitoring side, it's continuously monitoring the hardware status, so the power supply's temperature, reference oscillator status. It provides access to some important signal chain data like the ADC histograms, subband statistics, and the integrated power spectrum, all in real time. It also provides a status of the output stream. Yeah, Chris has already provided the evidence that it works, but just showing some lab test results. So this is the left-hand plot is the lag spectrum from the cross correlation of two gimbals, and the right-hand plot shows the integrated power spectrum from the internal FPGA spectrometer. So we've been really happy with the results in the lab as well as at the telescope, of course. One last thing that I'd like to point out, though, is that this has been a real workhorse of our instruments. So it's now the gimbal digital receiver is now targeted or currently used in a lot of our major projects. So it's the digital receiver for the Parkes cryogenically cooled phased array feed. It's the same identical hardware with a slightly different FPGA firmware. But the same hardware and identical firmware is used for the JPL Deep Space Network receiver package, and also the proposed upgrade for the Parkes ultra wideband receiver. So, thanks.
Question. Just a little, sort of one question. So what's the point of the 4 to 8 select? So why are you selecting only 4 of the 8? It feels just a bit.
Okay. So, yeah, that's back here. So we have space in the device for two dual polyphase filter banks, which can process 4 ADC channels at once. In the CryoPath variant of the gimbal hardware, we do process all 8. So the filter bank is slightly different, and the output transport is capable of processing or transporting all 8 inputs as well. Hey.
I was wondering if these boards will be available to people outside CSIRO in stage.
I would imagine so. I guess you've got some of the right people in the audience to answer that question better, but I think there are issues with export controls on the RFSOC device, which may require some negotiating, but I'd suggest maybe talking to Douglas or Mark.
Any other questions?
One behind you.
Thanks again.
This has got one.
There's not one comment, is that your last couple of plots I'm thinking of this. So this is traditionally, I think, in ATNF, we have not used standard transport protocols. With the gimbal, we've moved over to using 100 gig Ethernet. So a lot of this lab sort of stuff has been fantastic. We've been able to grab the raw data, raw voltages, right into disk, do all sorts of processing. I think that's been fantastic for actually debugging a lot of these things. So it's really, really flexible in terms of how we sort of do the lab testing. I think this sort of stuff makes really very simple software to process it.
Yeah, and having the Python software layer as well has made it extremely easy to work with, rather than C++, which was one of our previous systems. It's a lot more complicated.
All right, looks like we're setting down. So thanks again to all the speakers. And then that concludes the morning part of the session. We will continue again at 13:30. Same place. See you there.